Okay, I just want to take a few. Um, I just want to take a few. A few questions. So let's start. Quantitative. The good thing about quantitative chemistry is that you have some simple questions. Like if you look at the beginning of that paper, it says sodium carbonate NaCO3. So NaCO3. Today's date is what, 15th, right? 5. So Na2CO3. It says you should just list the number of atoms in sodium, carbon, and oxygen. So that's 3 questions. That's 3 marks. So it's simple, and these are simple. So you have 2 of those. You have 1 of carbon, and you have 3 of oxygen. So that's a giveaway. Now it starts getting to the one that students don't really like, to calculate the formula molecular mass. Even that one is easy. So you're giving sodium the same sodium carbonate. You're asked to then calculate the relative molecular mass. So you have sodium CO3. Now you're giving the mass numbers. Sometimes you will not be giving the mass number. If you're not, just check your periodic table. It's a bigger number. Yeah? Yeah, are we cool with that? The periodic number. So sodium is 23. So we times that by 2, that gives us 64. Then plus carbon, which is 12, is only 1. Oxygen is 16. If you times oxygen by 16 by 3, what does that give you? 48. So if you add all 3 together, that should give you a total of
104.
1 over. So 64 plus 12 plus 48. That's 4. You carry 1 there.
104.
That's, sorry? Carry 1, that's 7, 8 plus that's 124. So it's a total of 124. That's simple. So those are the simple ones. So did you not multiply by the base numbers? That's where students make mistake. You have to multiply by the subscript. If it's Na2, it's not just 1 sodium. It is 2 atoms of sodium. It's a molecule of sodium. So you need to multiply by 2. Now, if we look at the next questions, it says you have a student heated a sample of calcium carbonate. The equation for the reaction is this. So CO2. So calcium carbonate and then note this composition is using heat split up a compound. So that's a compound. If you dissolve it in water, it's not thermodecomposition. But if you use heat, if you apply heat to break it apart, then it is thermodecomposition. The other question says, both calcium carbonate and calcium oxide are white solids. The students weighed the white solid before and after. Explain why a decrease in mass was observed. So before thermodecomposition, yeah, they weighed it. They weighed CaCO3. At the end of the experiment, the weight, this one, there was a decrease. And we know by law of conservation of mass, there should be no decrease, isn't it? Yeah, but however, there was a decrease. Why? Because carbon dioxide was the second product. Carbon dioxide is a gas, so it escapes into the environment. So it escapes away. So that's why there's a decrease in weight. Now, if they're in mass, if, for example, it was a forming an oxide, say you were burning magnesium in air, or you were reacting zinc in air, it could increase. The increase is from the oxygen from the air. So you need to remember those. Then this is a very simple question. You have copper carbonate plus carbon equals to carbon and carbon dioxide. So one type of copper ore is mainly copper carbonate. When producing copper, the ore reacts with carbon. So you have copper carbonate reacting with carbon, and your end is copper plus CO2, written in what? So they've given you the amount in tons. This is 24 tons. These kind of questions are so easy, but I like to do them because I don't want you to just skip it skip it tomorrow because you think it's difficult. It's not. 264. What I just told you about, that's tons as well. So now they want you to calculate that. It's simple. Your arrow sign is your dividing position. So these are your reactants, these are your products. Your reactants should be equal to your products every time. That's the law of conservation of matter. So if you add those two together, 254 plus 264 gives you a total of how many tons? If we add that together, 9 and 5, yeah?
Yeah.
598, 5.
It's 518.
Okay, 518 because this is 11. Sorry, I took that to be 4. So 5 add 6 is 11. So it's 518.
Yeah.
If it's 518 tons and we already have 24 tons here, so what we just do is we do 518, take away 24. That's how we get the ton of that one. So it must balance out. So if you do 518 minus 24, what are
494.
494 tons. So these calculations are simple. They are simple. They are you find them on the foundation paper. Those of you that are doing higher and triple, you are good with your calculations already. My videos are to support people doing the foundation paper. Some of these things throw them off balance and they don't want to answer the question. So my revisions are very geared towards foundation. People taking the foundation paper because they're the ones that really need support. Most schools have plans and things in place how they support students who are doing triple and taking the higher. 1 minute, I'm just moving this closer. It's all right. Okay. So the next question shows a practical. It says a student did an experiment to find the relative formula mass. That's the diagram. If I put it close to the camera. At the end, they say the relative formula mass for each of them was given. You should calculate the mean. Remember, mean is just simple. You add all the numbers and divide by how many there are. Mean is one of the simplest things to calculate. The question went on to say that the experiments gave different results for the relative mass, formula mass of the gas. This was caused by an experimental error. What is the error? It has to do with gas. Gas, there could have been, it could have leaked, isn't it? So if gas has leaked, then the result will be affected. It was important to repeat the experiment, and this is a question that cuts across all experiments. Why is it important to do the repeat? When you do the repeat, you can calculate a mean. And then if you do it 3 times, say the third one was a complete anomalous number, you do it for the 4th time because you cannot have an anomalous number. It will affect your overall result. So you are able to calculate a mean. This is a 6-mark question. It says the relative formula masses for calcium carbonate for calcium carbonate have been given here. So the calcium carbonate is 100 for the masses. So for calcium carbonate is 100, and then you have calcium oxide is 56 plus carbon dioxide, which is 44. Now if you look at this equation here, it says you should calculate work out an experiment that you can use to provide evidence for the law of conservation. In this experiment, you need to explain what you're going to do. So if you take some of the calcium carbonate, take some of the calcium carbonate, then you take a boiling tube. You have to measure them separately. Use a scale to measure your calcium carbonate. Then you obviously measure your boiling tube. You note down the measurement. The reason is because you need to know the start mass before you start the experiment, right? Now, when you start working out this experiment, you have to use the tongue to hold the boiling tube over the flame. So as you burn it, you shake it a little bit, yeah? When you shake it a little bit, you let it cool for some time, and then you burn it again until a desired mass is, because when you burn it and you cool it, you weigh it again. Then you carry on, you repeat it until you get a desired weight. Now one of the focus questions they can ask you, or one of the ways you can ensure that you explain the law of conservation of mass. By the law of conservation of mass, the mass you start with should be the final mass that you're going to get. But that's not going to happen because this is not a reversible reaction. Those of you that are doing higher or triple, you know that when you're doing it with ammonia gas can recombine back to the two gases, nitrogen and hydrogen can recombine back to form ammonia. It's a reversible reaction. But this is not a reversible reaction. So when you get to the end of this experiment, you will not be able to prove the law that has disappeared by reason of the carbon dioxide that's produced. Do you understand? So the carbon dioxide will make it to be less than what you would have expected. And then you need to, it's a practical, remember to include your precautions, yeah? You have to be careful to make sure that, and this experiment is about thermodecomposition of calcium carbonate, by the way. That's what the equation is on the board. And then it says that a student made some copper sulfate crystals, yeah? The student used 7.95 gram of copper oxide and 100 centimeters cube of a 2 mole per dm cube solution of sulfuric acid, yeah? Now, they want you to calculate the what? Calculate the number of moles of copper oxide in that. So what you have to do, you have to calculate the relative molecular mass, yeah, of the compound. So which is calcium is how many? 63.5, and the oxygen is 16. But 16 times 3, isn't it? Yeah. But what are you the number of the calcium copper oxide, not this is about copper now. It's a different question. You have to calculate for copper oxide. Did you see it in the question? So it's the copper oxide that you are calculating. So your copper is 63, mass of copper is 63.5 and oxygen is 16, yeah? So that will give you 79.5. Now you have to use your gram that you're given, which is 7.95, to divide the molecular mass you've calculated. That's going to give you, use a calculator, that's going to give you how many moles? 0.1. So that's the mole, yeah? That's the value of the mole. So for the number of moles of sulfuric acid, cube of 2 moles per dm cube. 1,000. So anytime you see that question, always remember, don't overlook it. So it's 100 divided by 1,000, because that's your 1 dm cube. See that? And what's that going to give you?
0.1, I think. Yes.
0.1. Is it 0.1?
Yeah.
So you multiply it by the 2 you're giving. What's your answer there?
0.2.
No, it's not 0.2. What does that give you? Does that give you 0.2?
Yeah.
Okay. So that's what your answer would be. Okay. 0.2 moles. I'm looking at the question on I think those are the calculation questions. Is there any other one? Question 4. Hang on.
4.4.
No, let's look at 4 first. Have we done 4.1 and 2?
Yeah.
3 says it is common to use an excess of one reactant. So when you have 2 reactants here, it's common to use excess in making salts. The required practical of making salts. It's common that you use excess of copper oxide powder. You keep dissolving it until you have some black particles left. The reason is because you want to be sure that all the sulfuric acid have reacted. So if you are using an excess of one reactant, is to ensure that all the other reactants have fully reacted, been reacted in the compound. So for the next, the maximum mass of copper sulfate, you have already been given the moles. So you multiply it by the molecular mass you're given. So the moles that you're given is 0.25, isn't it?
Yeah.
So you are giving the mole as 0.25 moles. So and the molecular mass for is it sulfuric acid, a copper sulfate? Of copper sulfate is 159.5, 159.5. So you multiply the two, you multiply that with 0.25, and then you get the maximum.
39.875.
Yes, 39 point what? 39.875. Is that what you got?
Yes.
The question says it should be to three significant figures, so it's going to reduce to what? 39.9. Because the 7, you have to round it off to the 8. So if we look at the required practicals then, the required practicals are making salt. That's number 1. It was on the paper last year, so I don't know if this is going to be on this paper, but we can still look at it. They might ask it in a different way. It wasn't a 6-mark question of the foundation. So making salt, when you're making salt, you're making copper crystal salts from reacting copper oxide and sulfuric acid. This is a required practical. Making salts. So you're going to make copper sulfate salts crystals. So you need a copper oxide. Copper oxide is a black powder, and you need to react it to sulfuric acid, dilute sulfuric acid. So you have to measure a fixed volume of the sulfuric acid. Measure a fixed volume of the sulfuric acid and warm it gently in a beaker over the flame. Make sure it doesn't boil. Heated it up to ensure that the reaction is fast, goes quickly enough. Yeah, give it an activation energy. What you have to do, you then take some of the black copper oxide, powder, and put some in and stir it with a rod. When you stir it, it will disappear. Yeah? It will disappear and change it to a light blue color. You need to keep adding until there is no more can be dissolved. You'll be seeing some particles of the copper oxide in your solution. And then you use a filter paper to filter it off. So you have your liquid that you've collected in a conical flask. That liquid you've collected, you can now pour some into a petri dish, an evaporating dish, and put it over a beaker of water on the fire. So as the water is boiling, it will be allowing it to allowing it to evaporate, leaving the salt behind. So you don't have to wait until it's fully evaporated. You have to leave it like halfway. You put it down from the fire and let it cool gently. Because if it carries on boiling, it will start to spill out, and then you won't get your proper salt crystal. Okay? So those are the things that you need to know for the reaction making salts. How to make copper crystal salts. Okay? Whilst I'm on copper crystal, I just want to quickly remind you of how equation for salts generally. So I'll come back to regard practicals. Equation for salts generally. The name of a salt comes from the acid it's made from and the metal, isn't it? So if you have copper oxide, yeah, copper is already there, yeah, and you react it with hydrochloric acid, what will be the name of this salt? This salt is going to be copper chloride, okay, because it's from hydrochloric acid. If we have sulfuric acid, it will be copper sulfate. If it was nitric acid, it will be copper nitrate. So the name comes from the metal and the acid that you've reacted with. Okay, the second required practical is the electrolysis one. So the electrolysis okay, the electrolysis so for electrolysis you need the power source, yeah, the direct current power source is obviously going to be connected to your electrodes. So these two electrodes are negative and positive. So you have the cathode and the anode, and you have your electrolyte, isn't it? Your electrolyte is the liquid that's going to be split up. This is your electrolyte. So let's say it's copper chloride solution. Let's say it's copper chloride that you're splitting up, but there's also water, so you also have hydrogen ions here. So you have your copper ions and your chloride ions. So you have all of these. So because copper is positive, copper is going to migrate to the cathode. So you're going to end up with copper deposit on that one. Yeah, it will be glowing, so you know copper has a positive. Now the chlorine is going to migrate to the anode because it's positively charged, and chlorine is a negative ion, so it's going to migrate there. All right, now when the chlorine migrates, chlorine will be given off there. When you look at the copper and the hydrogen ions, right, they are both positive. So the reason copper was the one that was deposited and it was hydrogen is because copper is less reactive. It's less reactive than hydrogen. Hydrogen is more reactive than it. It's about displacement. Yeah, it should remind you of displacement reaction. So that is how the ions are formed at the different electrodes. These two are called the electrodes. So that's the required practical, and those are the kind of questions that they will ask on your foundation paper. The other one is disappearing cross practical. That's one of my favorite. That is reacting sodium thiosulfate. So sodium thiosulfate if you have sodium thiosulfate in different concentration, this is the rate of reaction, how concentration affects the rate of reaction, concentration and rate of reaction. So that's a required practical. Now if you measure a fixed volume, if I can draw what looks like a conical flask here. So if you measure a certain amount of your sodium thiosulfate here, yeah, you then measure the same. So let's say you had a 10 centimeters cube